Hello, this time real capacitors. A quick look at some capacitors and how their performance differs from that of the ideal capacitor that we use in simulations and simple circuit analysis. Here are some real capacitors. There's a ceramic capacitor there, a tantalum capacitor here, and here we've got a couple of electrolytic aluminium foil capacitors. Now, the body size of capacitors is often much larger than the body size of resistors, so we can be a little more helpful with the data that we can fit on a capacitor body. These large capacitors here not only tells you its value, in this case 10,000 microfarads or 10 millifarads, but also its safe operating voltage, 25 volts in this case and 100 volts in this case down here. Any of these capacitors will have a safe working voltage, and if you exceed that voltage, the capacitor can overheat. The chemicals inside the capacitor can start to boil, and it can explode in some fairly dynamic and impressive ways. Please don't try this at home. Smaller polarized capacitors, this tantalum capacitor here, for example, has not as much space to write things on. The 2.2 is the value of the capacitor, in this case 2.2 microfarads. The 25 is the working voltage, 25 volts. You just have to know that they're that way round. The plus sign there indicates which side of the capacitor is positive. For this capacitor here, we have a big arrow here saying minus, minus, minus. That points to this side here being the negative terminal. This is a ceramic capacitor. You can't really see from the scale, but it's a much smaller component than the other two, and it uses a similar naming scheme to surface mount resistors. The 105 is 10 times 10 to the power of 5, the 5 is a multiplier, picofarads. So 10 times 10 to the power of 5 would be 10 times 100,000, or 1 million picofarads. This is, in other words, a 1 microfarad ceramic capacitor. What differs in these different capacitor types is the material in between the two plates, and that contributes a different amount of polarization field. Remember that if you put an electric field across a dielectric material, a polarization field will be formed within the dielectric material, and that will act to reduce the effective electric field in the body of the material. And by looking at the capacitor equations and noting that the voltage, the potential difference, is the electric field times the difference, if we can reduce the electric field within a capacitor body, then we can reduce the voltage that corresponds to a certain amount of charge on the plates of the capacitor, and that effectively increases the value of the capacitor. So we can make larger capacitors in the same amount of volume if we can find a material to use which creates a large polarization field. And it's that material which makes the difference in performance and characteristics of the different capacitor types. This is a sort of a family tree of different common capacitor types. Of the non-polarized types here, ceramic capacitors are the most common ones. These have a ceramic material as that dielectric between the two plates. And you can get different ceramic materials with different properties. An NP0 class capacitor will have a comparatively small capacitance for a certain volume. However, the characteristics are very stable with temperature, which makes it a good choice if you're designing something like a filter, where you need the capacitance to remain reasonably constant across a wide range of operating temperatures. You can move up to other classes of capacitor, an X7R class, for example, which will give you a larger capacitance in the same amount of volume, and they're often cheaper as well. However, that capacitance is not as stable with temperature. In terms of the electrolytic capacitors that we're using this year, There's two main types, the tantalum capacitors and the aluminium electrolytics. We tend to use more aluminium electrolytics these days. There are some question marks over the long-term stability of tantalum capacitors. Aluminium electrolytics often tend to be cheaper as well. More recently, there are these polarized supercapacitors which have quite astonishing polarization fields inside them. You can get these particular materials which can reduce the electric field in the body of the capacitor by about 99.99%. And you can get very large capacitance values in very small volumes. You can even use these as replacements for batteries. You can charge them up much faster than you can charge a rechargeable battery. The main difference between a supercapacitor and a rechargeable battery is then that the voltage across a supercapacitor tends to decrease linearly as the capacitor discharges. However, the voltage across a rechargeable battery is ideally reasonably constant until the charge runs out and then it drops down. Now, in terms of the equivalent model, capacitors have leads and therefore an inductance in those leads. There is often a small series resistor as well due to the resistance in the plates and the leads, and a very large parallel capacitor due to some leakage from one plate of the capacitor to the other. Tiny holes in the rubber membrane if you think about the hydraulic model. At high frequencies, we can neglect the effect of the parallel resistor, and we use an equivalent model of the capacitor that looks like this. The series resistor, the capacitor itself, and a series inductor. Now, if you look at capacitor data sheets, what you'll often find specified is not the value of the series resistor or the value of the inductor, but the resonant frequency and something called the dissipation factor. The dissipation factor is the ratio of the real to the imaginary impedance, and it will be specified at a particular frequency. And you can work out what the value of the resistor is from the dissipation factor by noting this formula. The dissipation factor, the real impedance, well, that's just the value of RS itself. The imaginary impedance is going to be the total imaginary impedance due to the capacitor and the inductor. Now, a capacitor has a complex impedance of 1 over j omega c. An inductor has a complex impedance of j omega L. So if I express this as minus j over omega c plus j omega L, that is minus j 1 over omega c minus omega L. That would be the magnitude of the imaginary part of the complex impedance of this capacitor. And the ratio of those two is the dissipation factor, and that's what is often specified. But you'll see that in order to work out what the resistance is from the dissipation factor, you have to know the value of Ls, the parasitic inductance as well. And you get that from the resonant frequency. The resonant frequency is the frequency at which the capacitance and the inductance cancel out. So that would be given by 1 over j omega c plus j omega L equals 0. In other words, this is at the resonant frequency, I should say. I'll call it omega c. In other words, omega cl equals 1 over omega c times c, or the resonant frequency is the square root of 1 over Lc. So, if we know the resonant frequency, we can work out the value of the parasitic inductance, and if we know the parasitic inductance and the dissipation factor, we can work out the value of the series resistance. And then we've got our model for our real capacitor that we can use in simulations. If you plot the total magnitude of the complex impedance of one of these real capacitors against frequency, you will get this sort of curve, which we've seen before. At very low frequencies, it is behaving pretty much like an ideal capacitor. The value of the resistor here is very small compared to the impedance of the capacitor, and so is the value of the inductance. As you get close to the resonant frequency, the capacitance and the inductance tend to cancel each other out, and the value of the total impedance at the resonant frequency here is purely due to the series resistance Rs. And then above the resonant frequency, the value of the impedance due to the capacitor is smaller than the value due to the inductor, and the total impedance is dominated by the contribution of this series inductance. So at these very high frequencies, around about 100 megahertz and above, for this real capacitor, it's actually behaving like an inductor. Its complex impedance is positive imaginary, and it's increasing with frequency. Okay, that's all I wanted to say about capacitors. Next time, a quick look at inductors.